Welcome back to Real Analysis 1. In this lesson, we are going to establish the axiomatic structure of the real number line R. In real analysis, what we are ultimately interested in actually is looking at functions of a real variable. So we'll be talking later about functions, objects that you're used to working with. But before we do that, we want to establish a really rigorous idea of how real numbers and sets of real numbers behave, because these sets are going to turn into domains for those functions. And when we want to study the properties of functions, we need to understand how they behave on different kinds of domains. So that's the motivation for studying R, but I would actually say that real numbers can be amazingly interesting in their own right. So there's a lot of joy just to get out of thinking about the real number line. So we have a lot to talk about with real numbers. Here is what we are going to assume as fact right from the beginning. So these are our axioms. The first one is called the field axioms of R, basically saying that addition and multiplication work really nicely for real numbers, which is something that you've probably known for many years. The next one is the order axioms. R together with these two is something that we can call an ordered field, meaning that we have an idea of size. 3 is less than 4, -7 is less than -2, etc. So that idea that we can order the elements of the real number line. So we have that R is an ordered field. We'll do those fairly quickly because it involves operations that you are used to. The perhaps most interesting or exotic axiom here is the third one, and that is the completeness axiom. Ultimately, what this gives us, as we will not discuss completely in this lecture, completely get it. And what we will discuss in future lectures is that R, which we often think of as like a number line, really is this kind of connected piece. It doesn't have holes. It makes sense to draw it in this kind of sweeping motion from left to right. I'm not actually going to get into this as a consequence of the completeness axiom yet. In this lesson, I just want to state the completeness axiom. That's going to involve bringing in some definitions about sets. So let's jump right into this by talking about the field axioms. So here are the field axioms. I'm going to go through this fairly quickly. For field axioms, what we're saying is that R is a field. It's a set of elements. The elements are the real numbers themselves, together with addition and multiplication, so that these nice properties hold. There are other fields in mathematics. In fact, I'll mention one in just a minute. And I would say that R, together with standard addition and multiplication, is actually kind of like the model field. So these axioms tell us that these operations are nicely behaved on real numbers. And then we recognize that in other areas of mathematics, and we say, hey, look, this collection of elements with these operations behaves kind of like R with addition and multiplication. So R is like your model field, if you will. What we have here are these properties. I'm just going to write down quickly what they mean so that you know what each of these words is referring to. None of them are going to surprise you because I assume that you've been adding and multiplying numbers for a long time. The first property here is closure. What that means is that if you take two elements from the set of real numbers and perform either of these operations on them, you don't leave the set. So for example, if x and y are both real numbers, x plus y is also a real number, and so is x times y. That doesn't necessarily have to be true in a different environment. If you're looking at the set of imaginary numbers, it's not closed under multiplication because I squared is -1. That's real. So you can see the difference there. The closure is not always a property that you can assume with a set. The next property we have here is commutativity, so your ability to swap the order. X plus y equals y plus x times y is y times x. Commutativity is not always true if you study, say, matrix multiplication. So again, these operations are nicely behaved here with this set of real numbers. Associativity means if you take 3, you can kind of swap the order. These are operations that happen on pairs, not on triplets. So if you have something like x plus y plus z, when we write that, it makes sense to us because it doesn't matter if we do y plus z and then add x to that, or if we do x plus y and then add z to that. Technically, when you do addition, it's between the two objects. So it's like technically there is a sense of ordering here, but it turns out it doesn't matter because addition is so well behaved. Likewise, x times yz is xy times z. Okay, what are the identity elements for the real numbers? We have two operations here. We have two identity elements. The additive identity element, of course, is 0. X plus 0 is x. And thanks to commutativity, we can also flip that and say 0 plus x is x. Y times 1 is y. So we have an additive and multiplicative identity. We also have inverses for almost every number for both of these operations. All numbers have additive inverses. So if we have x plus negative x, we get 0. We get back the additive identity. So 3 plus negative 3 is 0. For multiplication, there's one exception. 0 has no multiplicative identity, but that's okay. It's built into the definition here. So y times 1 over y gives us back the multiplicative identity for all y, which are non-zero. Okay, so we can cancel out. And then we also have the distributivity property. We can distribute. And I think all I need to write down for this is x times y plus z is xy plus xz. Let's see, do I need any other phrase? Sometimes with distribution, it's like you want to say two things. I think this is enough. I'm sure somebody will let me know if I should have written down something else. So we can distribute in the way that you're used to doing. Okay, so the conclusion here is that with sets of real numbers, we have addition and multiplication, and they are very nicely behaved operations, meaning all of these properties hold just as you have kind of always felt or known to be true. We will treat this as an axiom. So that these are so well behaved is something that we will take as a fact to start with. Let me have you finish writing this down, and then we will look at the order axioms. Now let's run through the order axioms, again, visiting ideas with real numbers that you are probably very familiar and comfortable with. We are going to add to our ability to add and multiply numbers, our ability to compare them with inequality, so that these four properties are going to be true about our comparisons. The first one is trichotomy. So this is either x is less than y, or y is less than x, or they are equal. So one of these three things is true. And here this or is strict. Let me just make a little note of that. So you land in exactly one of these three categories. Like that. Okay, so again, that's something that you probably immediately feel must be true when you compare numbers. One is smaller than the other, or vice versa, or they're the same number. Transitivity is if x is less than y and y is less than z. What do you think I'm about to write down? Transitively, x is less than z. Okay, so we can compare numbers in a transitive way. Compatibility with addition means that if I take an inequality like this and I add the same number to both sides, I preserve the inequality. If x is less than y, then x plus z is less than y plus z. So that is compatibility with addition. Here it doesn't matter what kind of number z is. When we say compatibility with multiplication, we have to be aware whether or not z is, say, positive or negative. If x is less than y and z is greater than 0, I'm going to say greater, then xz is greater than yz, or if x is less than y, no, I am flipping my, sorry, let me flip this around. Okay. If x is less than y and z is positive, multiplying both sides of this inequality preserves it. So xz is less than yz, that's what I meant to write down. Or if x is less than y again, but this time z is negative, as we've known for many years, we're going to flip the inequality. So then xz will be less than yz. Okay. So those are our order axioms, just telling us that inequality behaves like you probably expected. Together, our ability to order real numbers and recognize that with addition and multiplication, that's a field, is telling us that R, it makes sense to call it an ordered field. R is the foundational, realm that we're going to work in real analysis 1. This ordering is actually special for R. If you think about it, if you look at, say, the xy plane, it seems like a nice set of numbers to work with if you have the xy plane, but it's not going to be ordered, right? It doesn't make sense to have the sense of inequality with, say, xy pairings around the plane. So R is really a special set. We have one more thing to establish about R, which compared with this group of observations in the field axioms might feel new. To go through our third axiom, the completeness axiom, I need to bring in some definitions involving sets. So we saw sets in the previous lesson where we just talked about sets of real numbers. Let me now define what it means to say that a set is bounded above, and that will lead us to the definition of something called the supremum of a set. So given a set A, which is going to be a subset of the real number line, we say that A is bounded above by some number B in R if whenever X is in A, then X is less than B or X is equal to B. Okay, I just wrote out something that we have a perfectly good notation for because we've talked about, numbers can be equal, X can be equal to B. We had this idea of ordering in the previous axiom set that we looked at, and now we'll say this notation, or sorry, this concept deserves its own notation. X is less than or equal to B. Okay. All right, so A is bounded above by the number B if whenever X is in A, then X is less than or equal to B. So B is greater than or equal to all of the members of the set A. If there exists such a number B, A is bounded above. Bounded above. Okay. So given a set A, we say that A is bounded above by a specific number B if B is greater than or equal to all of the members of A. If you could find such a number, then you can just say, hey, A is bounded above by something, by B. Okay. And this, I don't know if this is a strange concept. Things like N, Z, Q, these are not bounded above. However, if you look at something like A equals the numbers from 0 to 1, including 1, A is bounded above by 5. So 5, the number 5, is greater than or equal to all of the elements of A. If I took the set of negative counting numbers, it would be bounded above by 0. Okay. Not hard for you to take this and also create the notion of being bounded below. And if you are both bounded above and below, then your set is bounded. I'm actually going to dig into that a little bit more later, so let's just stick with this idea of being bounded above for now. If you can find an element in the real numbers which is an upper bound for the set A, and is somehow smaller, less than or equal to all other upper bounds, and that leads you to the notion of a supremum. So let me write that down. If A is bounded above, and let me actually add to this, and we call B an upper bound for A. Okay. Going back to this example, I said that 5 was an upper bound, but that's a random choice. 10 is an upper bound, 100 is an upper bound, 2 is an upper bound, 1 is also an upper bound. And somehow the number 1 feels like maybe the best upper bound, if you will. It's the closest to A is what it feels like to me, just looking at this example. And again, that's leading us to this notion of supremum. If what should I call it? Let's just call it x. If x is an upper bound, which I'll abbreviate UB, if x is an upper bound for A and x is less than or equal to B for all other upper bounds B, so let me write for any other upper bound B of A, this marker is giving up. So x is an upper bound and it's less than or equal to every other choice of upper bound that you could make. You call x the supremum of A. Supremum of A. And don't want to run out of room, but we have a notation for this. X is the supremum of A. You can say x equals the sup of A. So I would read this, x is the supremum of A, or x is the sup of A. That's pretty commonly said. Okay. So another phrase for this is least upper bound. I usually say supremum, but least upper bound really highlights in words what it is. It's the least upper bound. It's the smallest of all of the possible upper bounds. Again, for this set A here, it's not too hard to identify that the supremum of A is the number 1 because it is an upper bound. It is greater than or equal to all of the elements in A, and it's less than or equal to every other possible upper bound. Okay, this definition of a supremum of a set is going to lead us to our third axiom. So let me put that up in just a moment. So here is our final and perhaps most exotic axiom that we are going to build our understanding of the real number line off of. And this is the completeness axiom. There are different versions of this that you can build an equivalent understanding of the real numbers off of. So if you have a real analysis textbook or perhaps several real analysis textbooks, it's possible that they give you a different phrase here, but they should still identify it as some kind of completeness axiom. So there's not too much variation possible with the field axioms and the order axioms, but there there are alternative presentations of the completeness axiom, which again can lead you to the same place or do lead you to the same place. I like to use this version. It's called the supremum property. So using the notions that we just defined, any non-empty set of real numbers S, which is bounded above, has a least upper bound. This is an assumption that we are making. It's an axiom. So any non-empty set of S which has upper bounds has a least upper bound. Of course, we could also call this the supremum of S. The word completeness has a definition, and I'm not going to say yet what it is. I'd rather approach that after we've talked about maybe sequences. But let me go back to this idea I mentioned at the start of the lecture, where I said that R can be drawn like this continuous line without picking up my marker. Imagine for a second that it couldn't, and I had a hole in the real number line. This is not a rigorous argument, by the way. I'm just giving you an illustration of how this concept allows us to fill in the number line. So I just want to give you a working idea. We will revisit this idea. We have a lot of videos about the real number line to come after this. Okay, imagine that my set S was, say, here. I'll just pick kind of this set S. It has an upper bound over here. So by the supremum property, it has a least upper bound, and just the way I've drawn this picture, that should be here, right? But if I take, say, this element in S and this real number, so this real number and this one, and I average them, so add them together, divide them by 2, by closure, that should produce a real number, and it would land somewhere here, but I'm claiming by my picture that there are no real numbers there. So, this is a huge hole that I've just landed inside of. Perhaps a more interesting question for us to study is, could there be what look almost like single numbers missing, so much smaller holes. We'll return to this idea, but I just wanted to illustrate how somehow the soup is going to allow us to observe the real number line as this kind of continuous arrow that we always draw. Okay, I want to wrap up by just stating that R is an ordered field which is complete. The word complete for us right now is not fully defined, so we are going to say that it has the supremum property. Every non-empty set of numbers, which is bounded above, has a set supremum. So that's what we'll take as our sort of third understanding of R. I'd like for you to take a moment to compare R to the set of rational numbers. So R has this axiomatic structure we've given it. Decide if the same axioms apply naturally to a set of rational numbers. So does it make sense to say that rational numbers are an ordered field, which perhaps also has the supremum property? So just pause for a second. I'm going to come back and take you through this, and then that will be the end of this video. So here's the analysis that I wanted you to go through when I said compare Q to R through the lens of these axioms that we've been looking at. Is Q a field? Meaning if I take the set of rational numbers and equip them with the familiar addition and multiplication operations, do those properties hold? The behavioral properties, commutativity, associativity, distributivity, those are automatically going to hold because it's the same type of operation in the subset of real numbers. So if x plus y is y plus x for all real numbers, then that's also going to be true for rational numbers. Rational numbers have an additive and multiplicative identity because 0 and 1 are both rational. So we can say that rationals have an additive identity, 0 belongs to the set. They have a multiplicative identity, 1 belongs to the set. They also have inverses because if you take a rational number and negate it to study its additive inverse, that's going to be rational. Likewise, if you take a ratio of integers which is not 0 and flip it to get the multiplicative identity, then that is also rational. And also, the one that's quick to skip over, but you really have to check it, is closure. The sum of any two rational numbers is rational. The product of any two rational numbers is rational. That's not true for irrational numbers, so that is worth checking. So you do have to think about closure. So yes, this is a field. Rational numbers are a field. I said earlier that I would show you another one besides R, and here it is. It's ordered because it has trichotomy. So rational numbers are either one is smaller than the other or vice versa, or they're equal. All of the kind of behavioral aspects of inequality that we observed for real numbers or that we assume for real numbers will hold if we reduce down to the set of rational numbers. So rational numbers are an ordered field. If I take a set of rational numbers which is bounded above, does it necessarily have a supremum which is also in the set of rational numbers? So I didn't really emphasize too much here because we are working in R that the set supremum has to be a real number. That was illustrated here when we said there should be a real number, this canyon between my two kind of halves of the number line. And the answer is no. We forgot what the question was. Is it the case that if I take any set of rational numbers, which is bounded above, that it has a set supremum, which is also rational? Okay, and the answer is no. And what you can do is look at, say, a set S, which consists of decimal expansions of an irrational number. So taking as fact that, say, pi is irrational, if I let my set S be 3, 3.1, 3.14, I can only go out 4 digits. 141, 3.1415, ... So imagine that my set here, S, is a set of rational numbers which are the decimal truncations of the irrational number pi. This set is bounded above by the number 4. It's bounded above by the number 100, so it has upper bounds. But it actually doesn't have a least upper bound, which is a rational number. And that's because if you embed this back on R, you'll find that the set supremum for the set is actually the number pi. Let me write that down. So sup of S equals pi, which is not rational. Okay. I'm assuming a few things here. I'm assuming that pi is irrational. Finite decimals like this are rational. So I'm using some facts here that we're going to go through. But I just wanted to throw this up here as an illustration of how Q has kind of 2/3 of what we've discussed in this lecture. The fact that we have a set supremum here, which doesn't belong to the original set Q, is telling us that Q shouldn't be called complete. So that's, again, kind of our working understanding of what the word complete means. We have so much more to discuss. I just wanted to give you these axioms that we are going to build off of. Thank you for your attention.